Okay, let's take a look at chapter 7.11, which deals with predicting the products of substitution and elimination reactions. And if you look at the second point here, it says it should be clear that in many cases a mixture of substitution and or elimination products will be obtained. And that's the whole point of this section, which deals with determining what are going to be the major products, the minor products, and how do we determine um, what those are. So let's move on. So it says here that it is also possible that for a given substrate, like this tertiary alkyl halide here, that only one mechanism is going to occur. So in this reaction, there's only one product. So in order to understand how to use these reactions to transform alkyl halides into the desired compound, which is our goal, one must be able to predict all the products that will form in a given reaction as well as the major and minor products. So ultimately, our goal is going to be able to design molecules and to figure out ways to make them using our knowledge of reactions in organic chemistry. So predicting the products, how do we do it? We kind of take a three-pronged approach, if you will. So the first thing is going to be we're going to determine the function of the reagent. Is it a strong base, a strong nucleophile, weak base, weak nucleophile, etc.? Then we're going to analyze the substrate. Is it a primary, secondary, or a tertiary substrate? And then we're going to consider any relevant regiochemical and stereochemical requirements. Do I only get the Z isomer, the E isomer? Do I make the trans isomer, the cis isomer? Is this regioselective, stereoselective, stereospecific? Okay, so that's going to be the third part that we're going to have to deal with. So moving on from here, remember what kind of reagents promote SN1, SN2, E1, and E2 reactions. So I like to think that when I'm looking at bimolecular mechanisms, so SN2 reactions or E2 reactions, that's going to require either strong nucleophiles or strong bases. And when I'm doing unimolecular mechanisms, so SN1 or E1 reactions, that's when I'm going to use weak nucleophiles or weak bases. So it says here, the following table is a great resource for categorizing reagents and the mechanisms they will promote. This is the kind of thing that I would suggest memorizing or recommend even memorizing for the quiz coming up. But you'll find that the more practice you get with predicting the products of reactions, that you'll need less and less help with this. So we've covered most of these up till this point in the class, but there's a couple of compounds here, some new acronyms that I want to cover. They are DBN and DBU, both of which are strong bases, but they're weak nucleophiles. And the reason that DBU and DBN are weak nucleophiles is because they are so hindered that they can't attack an electrophilic center. So here are the structures of DBU and DBN. So DBN, the N stands for a nonene, so non, so that stands for 9 carbons. And then in DBU, the U stands for undecene, so that means it's got a total of 11 carbons. Anyhow, I'm not going to go over the nomenclature of DBN and DBU. Suffice to say that I won't ask you to draw these compounds, but you should be able to recognize them, recognize their acronyms, obviously, DBN and DBU, and you should know that they are non-nucleophilic strong bases. So, why are these strong bases? Well, if you look at just the example here with DBN, and you could draw a similar mechanism with DBU, that when they take a proton, so a base is a proton acceptor, so you see the mechanism here is that once it accepts that proton, the protonated form of the compound is resonance stabilized, which makes it a very good base. So that's enough about DBU and DBN, which are both non-nucleophilic strong bases. All right. So once you determine what mechanism will be favored by the reagent, you're going to analyze the substrate, and then you're going to see which mechanisms will dominate. So which one is going to be the preferred mechanism. So if you take a look at this table, there's a few generalizations you can get out of this table. Students like to memorize this table, and I don't think it's a bad idea. The book discourages it, but I think, for the first quiz that you try using this table, it might not be a bad idea. But if you look on just the left side of the table, that when we have a strong base, so whether it's a strong nucleophile or a weak nucleophile, that when we're dealing with strong bases, that elimination mechanisms are going to predominate, except for in the case where we have a primary substrate. In that case, substitution will dominate, but all the rest of the cases, elimination will dominate. And then another good generalization you can make from this table is if you're using a weak base, so whether it's a weak nucleophile or a strong nucleophile, the substitution is going to be the preferred mechanism. So whether it's an SN2 or an SN1 reaction. And a third thing that I usually, relate to my students is that substitution on the unimolecular or by a unimolecular mechanism and elimination in a unimolecular mechanism only happens for tertiary substrates. So only for tertiary substrates. Anyhow, again, the book discourages you from memorizing the table, but I don't think it's a bad idea. And it's one of those things that the more you practice it, the less you will need the table as a crutch as you move through the course. Anyhow, let's keep moving here. So the next few slides just basically deal with review about all the different types of mechanisms that we looked at, and just a few pointers to help you along the way. So it says here in the first bullet point, it says, after analyzing the reagent and the substrate, you can say which mechanisms are going to occur. Then you're going to draw all the possible regioisomers, stereoisomers. Then you're going to pick the major product using the guidelines that we've covered already in class. So if you have an SN2 reaction, that gives you only one product, but you have to remember that you have inversion of configuration at the alpha carbon. So that means if you have a stereocenter that's R, it's going to become S, and if you have one that's S, it's going to become R. So if you remember, that was like the umbrella flipping in the wind, which we covered in class. If you have an E2 mechanism, you're going to draw all the possible alkenes that could be produced by this elimination reaction, and only alkenes that result from a beta hydrogen that is anti-periplanar to the leaving group can form. So if you have a bulky base, the one I drew here is potassium or a T-butoxide. So this, what I've drawn here, is the same thing as T-butoxide. So if we have a big old hindered base like that, the Hoffman product, which is the less substituted alkene, that's going to predominate. Where if we use a non-bulky base like hydroxide or ethoxide, the more stable alkene, the Zaitsev product, will predominate. And if you remember, the Zaitsev is the more substituted alkene, the more stabilized alkene. All right. For an SN1 reaction, what you should do is you should draw the carbocation intermediate after the loss of leaving group. Then ask yourself, will this carbocation rearrange? If it doesn't rearrange, then you take the nucleophile, you attach it to the carbocation, and you're done. If it does rearrange, you should draw the resulting carbocation after the rearrangement. Then you add the nucleophile to that. If you have a chiral carbon, what happens? Well, if a chiral carbon is formed by attack of a nucleophile, then you're going to draw both R and S products. So instead of inversion of configuration like we saw in an SN2 mechanism, with SN1, what you get is racemization. So you're going to get a racemic mixture. So you're going to draw both the R product and the S product. So again, the product that results from retention of configuration and the product that results from inversion of configuration. All right. And then lastly, if you have an E1 mechanism, again, you draw the carbocation just like in an SN1 reaction. If it rearranges, draw the rearranged carbocation. Then draw every possible alkene isomer that you can get from the abstraction of a beta hydrogen. All possible alkene stereoisomers are going to form. E1 is not stereospecific. The major product in the case of an E1 mechanism will always be the Zaitsev product. So the Zaitsev product is always going to be favored over the Hoffman product when we're dealing with E1 reactions. So just to kind of wrap this section up, let's look at a problem. It says, predict the products of the following reaction and label the major product. So step one, let's analyze the reagent. We have sodium hydroxide. Sodium hydroxide is a strong base and it's a strong nucleophile, so that means it could participate in SN2 and E2 mechanisms. But then we have to examine our substrate, which happens to be a secondary alkyl halide, because if you look at our alpha carbon, here's our alpha carbon, it's attached to a carbon down here, it's got a carbon here and a carbon here, so that's a secondary alkyl halide. So SN2 reactions and E2 reactions can occur, but in this case, E2 is going to predominate. So now that we know that E2 is going to predominate, let's figure out what's going to happen in the rest of the reaction. So what does it say here? Because secondary substrates are somewhat hindered, backside attack is more difficult. That's something we would have covered in class already. So we get those things down. And then we're going to consider the regio and stereochemical requirements. So for SN2, for the SN2 mechanism, the backside attack is going to give you inversion of configuration, just like that umbrella flipping in the wind. So here's our SN2 product. So there we go. We've already figured out what one product of the reaction will be. So that's the SN2 product. But that's not going to be our major product, because we know when we have a secondary alkyl halide and hydroxide, which is a strong base and a strong nucleophile, that the E2 product should predominate. So we got to keep going. So for the E2 product, we're going to look for all the beta hydrogens that can be anti-periplanar to the leaving group. Then we're going to draw the resulting alkenes. So you can see on this carbon here in red, we have 2 beta protons, and on this carbon, I'll just use get out the green pen here. On this carbon, we have 3 beta protons, So when we have 2 beta protons on the red carbon here, that means that it's not going to be stereospecific. So that means that we can get both the trans isomer, so we can get the trans stereoisomer and the cis stereoisomer. And then even though this is the less substituted alkene, if I pull off one of these protons here on this beta carbon, I'm still going to get that product as well, and that is going to be the Hoffman product. So here we go. So which one of these 3 alkenes should be the major product? Well, if we keep moving, you can see here it says now we have all the products from our SN2 and our E2 reactions. Now label the major product. E2 is the major pathway and the base is not hindered, so the Zaitsev is the major product. Yes, both of these alkenes, both of these first 2 alkenes, they both have the same amount of substitution on the alkene, but this one is going to be the most stable isomer because it's the trans. So that's going to be our major product. And then all the other products are going to be minor products. In case you haven't noticed, though, there's a major mistake in this slide, is that this isn't going to be a product. Let me draw in the correct product, so we'll redraw our cyclohexane like this. And then we're going to have our hydroxyl, and then we have our inverted stereocenter there. So all these other products are going to be minor products. So that's an example of a reaction in organic chemistry where you have more than one product. In this case, we have 4 products. So again, you have to have a good knowledge of the 2 tables that we looked at, and that will help you decide what are going to be the major and minor products in substitution and elimination reactions.